Right now, sitting on your desk, you likely have a machine with an incredibly powerful multi-core processor. I mean, it had the computing capability to render 3D environments, edit high-definition video, run complex neural networks locally.
Oh, yeah, modern laptops are absolute beasts.
Right, but then if you open a web-based dashboard, load up a heavy data set, and click Analyze, there's a very good chance the entire user interface will just freeze, like it's 1999.
Yeah, the classic frozen screen.
Exactly. The cursor turns into a spinner, scrolling completely stops working, and you're just left staring at an unresponsive screen, wondering if you need to, force quit the tab.
We've all been there, impatiently tapping our fingers on the desk.
Today, we are exploring the invisible architecture that is finally fixing this exact bottleneck. Our mission here is to understand how modern browsers are, well, unlocking native-level parallel processing to turn simple web tabs into heavy-duty application powerhouses.
It's a huge shift in how we build for the web.
It really is. And we are pulling our insights today from a technical piece titled Web Workers by the technology writer Aaron Rose from tech-reader.blog. Okay, let's unpack this. If the hardware sitting in front of you is so powerful, why does sorting a moderately sized spreadsheet bring a modern web app to its knees?
Well, it comes down to a fundamental misconception about what is actually happening during that freeze.
Yeah.
Because in almost all of these scenarios, the application hasn't actually crashed.
Right, it just feels like it has.
Exactly.
Yeah.
And the calculation that caused the freeze, maybe it's parsing a massive CSV or running some complex aggregation algorithm. It might have only taken, say, 400 milliseconds to complete.
Which is less than half a second.
Right. So the problem isn't that JavaScript or the underlying V8 engine running it is inherently slow. The issue is purely about blocking.
Blocking the main thread, right?
Exactly. For those 400 milliseconds, the user interface was completely starved of computing resources.
Because of the single-threaded nature of the browser environment, we're talking about that main thread. It's kind of an architectural legacy, right? From back when web pages just displayed static text and maybe validated an email form field rather than running full-blown application logic.
Yeah, that's exactly it. The browser's main thread is responsible for executing all your JavaScript, but it's also responsible for calculating CSS layouts, doing garbage collection, and actually painting the pixels to the screen.
It's doing everything all at once.
It is. And to maintain a smooth 60 frames per second, the browser needs to update the screen every 16 milliseconds.
Oh, wow. So if your math takes 400 milliseconds.
You do the math. The browser just missed 25 consecutive frames.
Yeah.
The event queue just backs up. If the user clicks a button or tries to scroll, those events literally just sit in memory waiting for the main thread to finish its calculation.
I sometimes visualize the main thread like a restaurant operating with only a single employee.
Oh, I like that.
Yeah, like this one person has to be the chef cooking the complex meals in the back, and they simultaneously have to be the server waiting the tables out front.
Right, sprinting back and forth.
Exactly. So if they commit to cooking a massive 7-course meal in the kitchen, which is our heavy data aggregation, the dining room is completely abandoned. The customers can wave their hands all they want, but the server physically cannot respond until that entire meal is plated.
What's fascinating here is that every single data-heavy web application inevitably hits this exact architectural wall.
Every single one.
Yeah, pretty much.
Yeah.
I mean, you can optimize your algorithms, you can use more efficient data structures, but if the main thread is busy doing a synchronous calculation on, say, 2 million rows of data, it is mathematically impossible for it to process a DOM update at the same time.
Because it's locked up.
Right. The browser is rigidly following the rule of the event loop. The thread is busy, so the UI starves.
Which brings us to the solution Aaron Rose details in the source material. Basically, hiring a dedicated kitchen staff. If the single thread is the bottleneck, we have to move the heavy computation off the main thread entirely. And we do that using web workers.
Web workers are the game changer here. They give your application access to background threads. And to be clear, this isn't asynchronous faking,
What do you mean by faking?
like using a set timeout to just push work to the back of the queue. This is genuine OS-level parallel execution.
Oh, wow.
Yeah, you instantiate a web worker, and the operating system literally allocates a separate thread on a totally different CPU core to handle the logic.
So the main thread gets to go back to just focusing on the user interface, handling the clicks, the animations, rendering the DOM. Meanwhile, the worker is in the background just chewing through the data set.
Precisely.
But how isolated is this worker? Like, does it just share the exact same runtime environment as the rest of the page?
No, it is entirely isolated, and that is a critical technical boundary to understand here.
Yeah.
A web worker spins up its own separate JavaScript execution environment.
Completely separate.
Yes. It has its own event loop, its own call stack, and its own completely distinct memory space. Furthermore, and this is key, it has absolutely zero access to the DOM.
Wait, really? None at all?
None. The worker cannot directly read from an input field, and it cannot update a chart on the screen.
Okay, so going back to the restaurant, the chef is locked in the kitchen. They can't walk out into the dining room to hand the food directly to the customer.
Right, that would violate the health code, so to speak.
Haha, right. They have to pass it through a service window. And in the browser architecture, this is structured message passing. The main thread sends a message with the raw data payload. The worker receives it, processes it, and then fires an event back to the main thread with the finished result.
Structured message passing is literally the only bridge between the two environments. You use the post-message API to communicate across that boundary.
So what does this all mean? Should I just use web workers for every single click, network request, and calculation from now on? I mean, if isolating logic keeps the UI buttery smooth, it seems like we should default to putting all our business logic in a background thread and just treating the main thread as a dumb rendering layer.
You'd think so, but that approach actually leads to worse performance for most standard web applications.
Wait, why is that?
Aaron Rose is very specific about this caveat in the piece. Workers are not free. Instantiating a new web worker environment carries a pretty significant startup cost.
Like, how significant?
Well, the browser has to allocate a new memory isolate, boot up the whole JavaScript engine context, and establish those communication channels. This typically takes anywhere from 10 to 50 milliseconds.
Which in CPU time is an eternity.
Exactly. If the calculation you want to perform only takes 2 milliseconds to run synchronously on the main thread, pushing it to a worker means you just spent 50 milliseconds setting up the environment just to save 2 milliseconds of blocking.
Ah, I see. You've introduced a massive latency penalty for a micro-optimization.
Right. Plus, there is overhead in the message passing itself, which we will get to shortly. Workers only truly shine for sustained or substantial computation. They're designed for workloads that would noticeably block the main thread for, say, a tenth of a second or more.
Here's where it gets really interesting, though. What happens when the workload isn't just large, but massive?
Oh, this is the fun part.
Right. Let's say we aren't just processing a single batch of data. We're running analytics on gigabytes of local data. If we expand that restaurant analogy, instead of just hiring one sous chef to work in the background, we can hire 4 or 8 and assign each one a different station.
Now we are moving from simple offloading into true horizontal scaling.
Yes.
Aaron Rose provides a really concrete example of this in the text. Imagine that same web dashboard, but instead of a standard monthly export, you're analyzing 10 years of sales data simultaneously.
That's a lot of data.
You're looking at 5 million rows of raw data that need to be filtered, aggregated, and mapped to a visualization.
Doing that sequentially on the main thread without workers is catastrophic. I think the article notes an operation like that could freeze the user interface for 8 excruciating seconds.
Which is unacceptable today.
Totally. In modern user experience terms, 8 seconds of an unresponsive screen means the user assumes the application is broken, they are mashing refresh, or they're just abandoning the tool entirely.
But with workers, we can implement a MapReduce pattern locally, right in the browser.
Yeah.
You check the user's hardware capability using navigator.hardware concurrency to see exactly how many logical processors are available.
Oh, so you can adapt to whatever machine they have.
Exactly. Let's say they have a standard quad-core machine. You spawn 4 parallel web workers in the background. Because you have 10 years of data, you programmatically chunk the dataset, assigning each worker a different 2.5-year range to process simultaneously.
So they all execute their respective filters concurrently on different CPU cores. And because of that parallel execution, that massive 8-second calculation drops down to roughly 2 seconds.
Yeah, a massive speed up. But honestly, the reduction in total processing time is actually secondary to the user experience benefit here.
Really? How so?
The critical victory is that throughout those entire 2 seconds, the main thread was completely unburdened.
Oh, right. The UI never blocked for a single millisecond.
Exactly. The user could still scroll the page, hover over tooltips, or even click a cancel button to abort the operation if they change their mind.
That is a huge architectural shift. We are achieving vertical and horizontal parallelism entirely for free, right on the user's local machine, without ever making a single network request to a cloud server to do the heavy lifting.
It's incredibly powerful.
But, fixing the CPU bottleneck immediately exposes the next weak link in the chain. Because if we try to push 5 million rows of data to these workers all at once, we hit a memory limit. Loading an entire gigabyte-sized CSV file into the browser's RAM in one go will trigger a memory crash long before the parallel processors can even finish their job. The JavaScript garbage collector will just panic.
It absolutely will.
Huh.
The V8 engine has strict heap limits to prevent a single rogue tab from taking down your entire operating system.
Which is a good thing.
Right. But if you treat massive data sets like a single block of memory, the application will simply terminate with an out-of-memory error.
So how do we prevent the memory overload while still feeding the workers? To use an industrial analogy here, is this like an assembly line? Like, you don't dump 10 tons of raw steel onto the factory floor all at once and expect the machines to navigate it. You use a conveyor belt to hand off individual components to the robots one by one. The total volume of material moving through the factory is massive, but the actual footprint on the floor at any given second is highly controlled.
Yeah, it maps perfectly to the architectural solution Aaron Rose outlines next, the Streams API.
It's dreams, right?
To build a robust local data pipeline, you must combine web workers with streams. The Streams API is fundamentally designed for memory efficiency through backbrusher and chunking.
So instead of doing a massive, file-reader.redis text, call it swallows the whole file whole, you stream it. You read the file from the user's local disk, chunk by chunk. That stream is our conveyor belt.
Exactly. As each small, manageable chunk of binary data arrives from the disk, you immediately pass it via a message to your web worker pool.
Okay, so the worker gets it.
The worker receives the chunk, performs its heavy computation, say parsing the CSV strings and updating an aggregate total, and then it simply discards the raw string from memory. It sends a tiny progress update back to the main thread and grabs the next chunk from the stream.
And the brilliance of this architecture is that the entire 5 million rows never exist in the browser's memory at the exact same time. The data just flows through the application's architecture like water through a pipe.
That's the beauty of it. The memory footprint remains relatively flat, whether the file is 10 megabytes or 10 gigabytes. The file is streamed from disk, avoiding memory bloat. The chunks are routed to background workers, avoiding UI blocking. And the computation happens in parallel, maximizing the CPU.
It's the perfect pipeline.
As Rose points out, when you combine streams and workers, you build a local data pipeline that is virtually unstoppable by traditional web browser limits.
But, and I know there's a catch here, there is a hidden performance trap in how the main thread hands off those chunks to the worker. We established earlier that the main thread and the worker are in completely isolated memory spaces, right? They communicate via structured message passing.
Right.
When the main thread sends a chunk of data over that bridge, the browser doesn't just let the worker look at the original data. It relies on something called the structured clone algorithm.
Which is, unfortunately, the core performance bottleneck of standard message passing. Because the memory environments are isolated to prevent conflicts, standard message passing requires serialization.
Serialization?
Yeah, the browser takes the data on the main thread, serializes it, copies it across the OS boundary, and then deserializes a perfect clone of it inside the worker's memory space.
For a small, JSON object, the cloning process is negligible. But if our stream is handing off massive megabyte-sized binary buffers, like an array buffer representing raw image data or a huge block of uncompressed text, cloning it is disastrous.
It really is.
The CPU spends more time executing the copy operation than it does analyzing the data, and suddenly you've doubled your memory consumption because two identical copies exist simultaneously.
This is exactly where we have to bypass structured cloning entirely. The source introduces a mechanism called transferable objects.
Transferable objects? How do they work?
Instead of cloning the buffer, the browser can physically transfer the underlying memory pointer from the main thread's memory space directly into the worker's memory space.
Okay, but the article is super explicit that when you utilize a transferable object, the main thread entirely loses ownership of that buffer.
Yes, completely.
The moment post message is called with a transfer array, the original variable on the main thread is neutralized. If you try to read its byte length or access its data on the main thread on the very next line of code, the JavaScript engine just throws a runtime error. Giving away complete ownership feels inherently dangerous from a development perspective.
It feels strict, definitely.
Why enforce such strict detachment? Why not just share a copy or share the pointer so both environments can read it?
Well, it's enforced to prevent one of the most notoriously difficult bugs in computer science, race condition.
Oh, race conditions, right.
Remember, the main thread and the web worker are running concurrently on different CPU cores. If they both held a pointer to the exact same memory address, and the worker was mutating the buffer while the main thread was trying to read it to update a chart.
The application would encounter corrupted data or just crash entirely. It's a synchronization nightmare.
Exactly. So the browser's architecture forces a complete transfer of ownership to maintain thread safety without locking. By transferring the object, the main thread mathematically guarantees it cannot interfere.
The worker just assumes full exclusive control.
Right, and the performance benefit is immense. There is zero copying, zero serialization overhead, and the memory footprint doesn't increase by a single byte. It's an instantaneous handoff.
For 95% of high-performance web applications, transferring ownership of an array buffer is basically the absolute peak of the optimization mountain. You get maximum throughput safely. But Aaron Rose doesn't stop there. He dives into the 5% of use cases where you actually do need multiple threads to access and mutate the exact same memory at the exact same time.
And this is where browser architecture starts resembling like really low-level systems programming. For those extreme edge cases, developers can use a shared array buffer.
A shared buffer. So we are intentionally giving both threads the same pointer and risking the race condition.
We are, but we manage that risk using a specific set of tools called atomics. Yeah. When you use a shared array buffer, both the main thread and multiple workers can read and write to the same memory addresses simultaneously. To prevent them from corrupting the data, developers use the atomics object to enforce hardware-level synchronization.
Wait, how does that actually work mechanically?
Atomics provide methods like atomics.wait and atomics.notify. They basically act as mutex locks.
Okay.
If worker A is writing a calculation to a specific index in the shared buffer, it uses atomics to lock that address. If worker B tries to read it, the CPU physically pauses worker B's execution until worker A releases the lock.
Oh, wow.
It ensures predictable, sequential access to shared memory, even when the threads are operating in parallel.
That is essentially C++ style multi-threading, complete with manual lock management exposed directly inside JavaScript. The complexity of managing shared memory locks is immense. I mean, most developers building standard web dashboards will probably never touch atomics, but the use cases for it are rapidly expanding, right?
Oh, they definitely are. You see, shared array buffer utilized heavily in web-based video editing software, real-time audio synthesizers, and complex 3D gaming engines via WebAssembly.
That makes sense.
And increasingly, it is the foundation for running local AI inference directly in the browser. When you run a large language model locally, you have a massive weight matrix that needs to be accessed by multiple parallel processing threads constantly. Transferring ownership back and forth is just too slow. They need shared coordinated access.
The fact that we are casually discussing local AI inference, hardware-level mutex locks, and true multi-threading happening inside a standard browser tab, it really reframes what a web page actually is today.
If we connect this to the bigger picture, Aaron Rose synthesizes these capabilities into what he defines as the 4 pillars of a local-first architecture.
The 4 pillars?
Yes. When you understand these pillars, the distinction between a website and a native desktop application essentially evaporates.
Let's walk through that architectural shift. Because traditionally, a single-page application acts as a thin client. It holds the UI, but it relies heavily on network requests to a cloud database to read files, run queries, and process logic. The local-first architecture flips that model entirely.
Exactly. Pillar 1 is the File System Access API. The browser no longer just accepts uploaded files. It can maintain direct read-write access to a directory on the user's local hard drive.
Okay, pillar 1.
Pillar 2 is IndexedDB, which provides robust, structured local data storage capable of holding gigabytes of state without needing a remote Postgres server.
So you have the file system and the database.
Right. Pillar 3 is the Streams API, which we covered, allowing the application to parse massive local files with a minimal memory footprint. And Pillar 4 is Web Workers.
Web workers are really the engine that makes the other 3 viable. You can have all the local data in the world, but if processing it blocks the UI, the application feels broken. Workers provide the computational bandwidth to actually query the local database and parse the local files while keeping the rendering thread completely clear.
It all works together perfectly.
When you combine those four pillars, you aren't really building a website anymore. You are distributing a compiled, multi-threaded application that utilizes the user's own hardware for compute and storage, just wrapped in a browser sandbox.
And it drastically reduces infrastructure costs for developers because the server is no longer crunching the data. And for the user, it means the application works offline, processes data instantly without network latency, and keeps sensitive data entirely on their local machine.
It's an incredibly empowering shift for both privacy and performance. But the article leaves us with a final concept that pushes this even further. Once you have multiple web workers crunching data locally and your interface is perfectly smooth, the next architectural challenge is state synchronization across multiple tabs.
Right, the multi-tab problem.
If I have the dashboard open in 3 different browser windows, how do they stay in sync if there's no central cloud server acting as the source of truth?
Well, in a traditional architecture, tab A sends a payload to the cloud via WebSockets, and the cloud broadcasts it down to tab B and tab C.
Exactly. But Aaron Rose mentions the Broadcast Channel API. This allows multiple tabs from the exact same origin to communicate directly with each other, peer-to-peer, entirely on the local machine.
Without the server.
Without the server. Tab A can broadcast an event, and Tab B receives it instantly, without a single byte of data ever leaving the laptop. So think about the full scope of what we've unpacked today. If a browser tab can directly read the local file system, query massive local databases, run complex machine learning models in parallel background threads, and seamlessly synchronize state across multiple windows, all with zero network latency and zero cloud compute costs, what does the future of the cloud look like when our personal laptops are secretly supercomputers?
It really suggests a future where the cloud returns to being primarily a tool for distribution and backup rather than the bottleneck for real-time computation.
The era of the thin client might actually be ending. So the next time you load up a heavy dashboard, hit Analyze, and watch the charts update while the interface remains buttery smooth, you'll know exactly what's happening beneath the surface. You'll know the main thread is just waiting tables, while a highly optimized, multi-threaded kitchen staff is doing the heavy lifting in the background. The spinning cursor of death is increasingly a relic of bad architecture. Thanks for joining us on this deep dive. We'll see you next time.